Okay, let's do this projectile motion review. Black is not working anymore in this pen. We shall use blue. Alright, so soccer goalie makes a save and then kicks the ball through the air to the middle of the field. So we're talking about like a ground-to-ground kind of kick, like that. Graph the horizontal component of the ball's motion while in the air. I think this should remind you of the lab, right? Projectile ball. So if we say that the starting position of the ball is 0, then the horizontal part is constant velocity, like this. Now we can debate about whether it really started at 0 and like which is the positive direction, but what has to be true for this to be correct is it has to be a straight line, not horizontal, because the position is increasing same amount over the same intervals of time. So any straight line here except for horizontal would be acceptable. Now here in the horizontal direction we have constant velocity. The slope of this is the same, it's just a straight line, so that is going to look like this, constant velocity. If for whatever reason you decided to make your ball go the other way, that's okay, but this would have to be down here, right? It has to match up. Whatever the slope of this is, that would be where this line, the horizontal line, is. And in the horizontal direction, we don't have any acceleration. There is 0 acceleration, right? In the vertical direction, we have constant acceleration. So in the vertical part, our ball, if we say it starts at position 0, which is up to you, but why not? It goes up, and then it comes back down again like this. This is the vertical position. The velocity is the slope of this. So it starts with some kind of positive slope, and then here, that's the peak of it, where the velocity would be 0, and then it starts to go down, have negative velocities, and we know that this is going to be a straight line. And then the acceleration, what's the slope of this line? Well, if we're doing this, if this is an earth soccer goalie, then the slope of this would be about -10. That's the acceleration in the vertical direction. You should study those. Probably going to put that on the test. Something very similar to it. Just watch out for what the starting velocities are, right? It doesn't always have to be ground to ground. It could be a variation on that. All right. What's a force diagram for the soccer ball while it's in the air? The only force acting on it when it's in the air, if we ignore air resistance, is force of gravity. Motion map for the soccer ball's trajectory. So the key for the motion map is in the horizontal direction, we're going to space evenly. I think I'll go every 3 squares, like that. And then in the up-down direction, we have bigger spacing at the beginning, and then because there's downward acceleration, it's going to make those smaller until it gets to the top, and then bigger spacing, like that. So it should outline the trajectory. So let's see, 3, 2, 1. What if I do like 4? So I'll make this my first one, and then I'm going to go over to here. I'm always going to go over 3 because the horizontal velocity is constant. And then for the first one here, I'll go up by 4, and then I'm going to go up 3. That's not going to come down in enough time. So then I'll go up, how about 2, and then I'll go up 1 more, and then I'm going to go back down 1, and then I'm going to go down 2, and then back down. There, that looks nice. All right, see how the spacing in the vertical direction is big space, smaller, smaller, and then getting bigger as it comes back down because of the constant acceleration. So these are all the same length, right? I'm going like halfway to the next dot. And then in the vertical, halfway to the next dot, that's going to be 2 there, just 1 here, half a 1 here, and half 1 here, 1, sorry, I'm supposed to go down to there, and something like that. Right? So if you had to do this on the test, what I would be looking for, even spacing in the horizontal direction, and the spacing that starts big, gets small, and then gets big again for this ground-to-ground kick. All right. Tom the cat is chasing Jerry the mouse. You ever see the Tom and Jerry cartoons? Pretty old. When I was a kid. Across the table, it's 1.5 meters high. Jerry steps out of the way. Last second, Tom slides off. So this is a horizontal launch problem. So if you wanted to make a picture of it, that's my cat, and this is 1.5 meters up, and he is going to go sliding off the table at 5 meters per second, horizontal launch. Where will Tom strike the floor? What's the vertical and horizontal components just before he hits the floor? Okay, so I'm going to set up my info, my list. You've had lots of chances to practice doing this. Hopefully you're getting, I don't know, pretty comfortable doing it, I hope. All right, acceleration, -10 meters per second squared. What's the initial velocity? This is a horizontal launch problem, and this is the vertical column, so there isn't any. None of this launch velocity is vertical. All of it is horizontal. If you got to launch at an angle, then you're going to break it up and put the sine and cosine pieces here. What's the final velocity? I don't know, but I think I'm going to need to find it to do B. For what's the delta y, it is negative, because he's going down, -1.5 meters. And that is enough information right there for me to do this. The VI is 0, so don't need that. So you could graph that if you want, if you like that method the best. This one's pretty easy to do, a little bit of algebra, and get the time that way. So the time is about 0.55 seconds. And we need that information. It's not actually the answer to part A. For part A, I need delta x. So Vx is 5 times the time is 0.55. That's about, I'm going to round it up to 2.8. You round different than me, that is fine. Okay, what are the vertical and horizontal components just before he hits the floor? So I know what the horizontal is. The horizontal velocity is 5 meters per second. It's always the same. To find the vertical part, that would be the final velocity right when he gets to the floor, so at that time. So what equation do you want to use now? Well, I've got 4 of these things, so any equation with VF in it will work. And the easiest one is, in my opinion, is this one, because it's all set up VF equals. So VF is going to be -10 times 0.55 plus the initial vertical velocity is 0. So the VF is -5.5 meters per second. So what are the vertical and horizontal velocity components just before he hits the floor? It's these. This is the horizontal, and this is the vertical. I don't need you to label them more than that. That's fine like this, because we know, we all have agreed what this Vx is and what the Vf is. So we're good. All right. Number 3, lacrosse player slings the ball at an angle of 30 degrees above the horizontal with a speed of 20 meters per second. How far away should a teammate position herself to catch the ball? So we're going to assume that the throw height and catch height are the same, so the delta y is 0. So if you wanted to make a picture, it's just like a ground-to-ground kind of toss. And we're looking for how far? We're looking for that delta x. Now, this is a launch at an angle, so I'm going to have to go ahead and take that 20 meters per second and break it up into the Vx and the Vi, right? Alright, so doing that, this is going to be 10 because the sine of 30 degrees is 1/2. You can do that in your calculator, of course. And the 20 times the cosine of 30 is 17.3. So this is a vertical, and it's up. This is horizontal, constant. All right, so notice, where did this 20 go? Nowhere. It's an angled launch problem. That number is not going to show up over here. You got to break it up into the two pieces. Okay, what else do we know? It's a throw height equals catch height. It's a like ground to ground kind of situation. So the delta y is 0. And we should be good to go now, right? So delta y equals 1/2 at squared plus vit. And vi is, and so that's going to be, you can graph that if you want. It's possible to algebra that one, not too hard. That is going to be equal to 2 when you do that. If you need more practice or you want to have a little bit more time watching me do the calculator, the graphing thing, there's plenty of examples in the assignments in this unit. You can go back and find those. And then I'm going to bring that time over here. So delta x equals Vx times time. That is 17.3 plus, what? Just kidding, times 2. And that gives us about 34.6 meters. That's where the teammate has to stand to catch that ball. Somewhere around there. All right. Ball is thrown straight upward and returns to the thrower's hand after 3 seconds in the air. So this is another going up, back down again like this. So the delta y would be 0. All right, delta y is 0 after 3 seconds in the air. A second ball is thrown at an angle of 30 degrees with the horizontal. At what speed must the second ball be thrown so that it reaches the same height as the one that was originally thrown this way? Well, let's just focus on this for a minute and see if we can figure out what this VI is, and then we'll go from there. This is a little bit of a tricky problem here. I think if this showed up on the test, it would be probably the hardest problem. This is hard. It's not, you'll see once we understand what we need to do, that's not hard. It's the figuring out what you need to do that's hard, because it's not just like a straightforward horizontal or angled launch problem. Okay, so I'm going to try to figure out here what this VI would need to be for this to go up and come back in 3 seconds. So oops, I have the time there. We don't usually have that time, but in this case we do. So it looks like my VI is going to be, what, 15? Let's see. Let's just do the math here, not mess it up. Yeah. So my VI is 15 meters per second. Now, at what speed must the second ball be thrown so that it reaches the same height as the one thrown vertically? Well, if you're going to do an angled launch at 30 degrees, then this right here, just like when we did this problem, we took the launch, like the speed of that toss, and then we broke that up into the two pieces. And once we have that piece, the vertical thing is, I mean, it might as well have just been thrown straight up in the air, right, in terms of time and all this other stuff. So that means what we just found here, we're just kind of going at this from the other side of the problem. This 15 meters per second, that must be this. That's the initial vertical velocity. And that goes right there. And then what would the horizontal part have to be? I don't know, and actually I don't really care because I'm trying to find this, right? What's the speed that the second ball must be thrown at so it reaches the same height? Well, I know it has to have the same vertical component. So what's the trig that relates to these things? Well, sine of 30 is equal to opposite over hypotenuse here, right? That's what I'm looking for. So if I do a little algebra, move my hypotenuse over here, divide 15 by the sine of 30, I'm going to get 30. So, and maybe you recognize that it's a special right triangle or whatever from geometry. That's fine. Just do the math. So 30 meters per second is the speed it would have to be tossed at to match the same height as this. Number 5. Two objects are initially the same height above the ground. Simultaneously, one is released from rest and the other is shot off horizontally with an initial speed of 2.5 meters per second. So one of them is going to get dropped, and the other one is going to be kicked off horizontally like this. Now those two things are going to hit the ground at the same time because they both have an initial vertical velocity of 0. This is all horizontal. The two objects collide after falling 20 meters. So let me just put this one's going to go like this, and then this one's going to be dropped. So we'll put it maybe about here. So that one will fall to that same spot. And this is 20 meters. I drew kind of like ground there. There might be ground there. There might not, but we just know that they're going to be at the same place after falling 20 meters. How far apart were they to start with? That's like a delta x, right? From here to here. What's that delta x? All right, so I mean, if this seems a little bit confusing, kind of like number 4, this is like this one isn't super hard. It's a little tricky maybe to figure out what you need to do at the start. But I mean, you know, what else are you going to do? Start setting up your columns of information here, right? Because that's what we do. That's how we do these problems. So even if you're not 100% sure that you know where you're going with this, you set it up and start writing stuff down and see what you can do. Okay, so what can we do here? Horizontally, this is a horizontal velocity here, right, for this one, and its initial vertical velocity is 0. It's shot off horizontally. Horizontal launch, nothing here, all of it goes there. Okay. What is the delta y? Well, they're going to collide after falling 20 meters. Falling 20 meters. And that's enough for me to find a time there, isn't it? So delta y equals 1/2 at squared plus vit. So it's going to be 2 seconds, right? And that means that that horizontal distance that separated them is 5 meters. That's all. So once we start to set it up, then, you know, things fall into place. And finally, we got our launched angle with not ground to ground. So let's see, 35 degrees. I'm going to have to break that into the component parts. That's going to be my Vx, that's going to be my Vi. That launch velocity is 18 meters per second. So let's go ahead and just do that right now. I have to do 18 sine 35 and 18 cosine 35. So the short one's 10.3 and 14.7 is the long one. 10.3, 14.7. Looks good. So in the vertical direction, horizontal direction, what's the VI? That's the initial vertical velocity. It is 10.3 meters per second in the up direction, so that's positive. What's the VF? Don't know, don't care. What is the delta Y? 6 meters above the ground. So what's happening here? It's being this bored in with, sorry about the double preposition confusion there. I just imagined you were sitting in history class. Bored with history class. Bored in, you could choose either one of those, in or with, but probably not both. So here's the window, right? And I'm going to throw the book. Oh, I guess it's getting thrown like this. 18 meters per second at this angle of 35. And then this is 6 meters. So the delta Y is going to be 6 meters down. It's going to end up on the ground. The Vx, that is the 14.7 meters per second. And that is all I know for now. I can find the time over here, bring it here, and then how far from the building, looking for that delta x. This is just totally standard, classic, just like your projectile launch practicum, like many problems that you have done. I think we are definitely going to have to do graphing for this one. Minus 6 minus 5t squared plus 10.3t. So I'll bring that 6 over. And that's going to be 10.3. Oops. There we go. And then add the 6 over to the other side. And that looks good, but before, I haven't used this calculator in a couple of days, so I'm just going to look at my window, make sure that I'm good. 0 to 10, that's good, and then the y min and the y max just has to be some negative to some positive so I can see it crossing over. So that looks good. There it is, crossing, looks like between 2 and 3. Second, calculate, 0. And I'm just going to do 0 to 10, because I know it crosses in between there. And guess 2.53. All right, and then last thing to do is delta x equals Vx times t. So 14.7 times 2.53 is 37.2 meters. Pretty good toss. All right. That's all. That's your review.